What's up, everybody? Welcome to the CVPR pre-show, sponsored by Voxel 51. I'm your host, Harpreet Sahota, a hacker in residence at Voxel 51. I'm joined by my co-host, Jason Corso, co-founder and CSO at Voxel 51, and a professor of robotics, electrical engineering, and computer science at the University of Michigan. We're here today with Catherine He and Dr. Paola Cascante-Bonilla. Catherine is a first-year computer science PhD student at Rice University. Before this, she obtained a BS in computer science from the City University of Hong Kong. Her primary research interests lie in computer vision, focusing on efficient algorithms under less or multimodal supervision. She is particularly interested in leveraging neuroscience and cognitive psychology to help develop concise, efficient, and interpretable algorithms that achieve human-level intelligence in versatile tasks. Dr. Cascante-Bonilla received her PhD in computer science at Rice University, where she worked on computer vision, natural language processing, and machine learning. She has focused on multimodal learning, few-shot learning, semi-supervised learning, representation learning, and synthetic data generation for composability and privacy protection. Her work has been published in machine learning, vision, and language conferences. We're going to discuss their paper, Improved Visual Grounding Through Self-Consistent Explanation. Their paper introduces a method called SelfEQ, which improves visual grounding in vision language models without bounding box annotations by fine-tuning the model to generate self-consistent attention maps for equivalent text phrases. Using automatically generated paraphrases and a weakly supervised objective, SelfEQ significantly outperforms prior methods on benchmarks like Flickr 30K and Referit. I hope you're excited to talk about their paper and discuss the work. Let's get right into it.
Thank you, Harpreet. Thank you for the opportunity. It's my great honor to present my paper. So today I'll present our CVPR 2024 paper, Improve Visual Grounding Through Self-Consistent Explanations. Vision and language model trained on image text pairs shows strong localization capability through gradient-based visual explanations. For example, the LBAP model excels in visual grounding using visual explanation methods like RedCam. But how can we improve localization without region annotation? Consider the example in the figure. Previous model can localize frisbee but struggle with less common reference like disk. Our SelfEQ promotes consistent visual explanation for paraphrase prompts, expanding the model's working vocabulary and improving localization performance without region annotation. We generate paraphrases using an LLM and propose the self-consistency equivalent tuning objective to ensure consistent visual explanation for paraphrase input text pairs referring to the same object or region. We input image text and image paraphrase pairs to our base VLM. We then obtain gradient-based visual explanation. We assume a self-consistent VLM should produce nearly identical attention maps for both the original text and its paraphrase. To achieve this, we minimize heat maps L2 distance to make them more similar.
While minimizing a sum of pixel-wide distances contributes to self-consistency, without regularization term, this loss can easily lead to trivial solution. To address it, we integrate these heat maps by defining an ROI mask. We observe that if the sum of attention scores at a given position exceeds a certain threshold K, it is likely to indicate a correct prediction.
We propose a consistency loss expecting the ROI region of the attention maps to achieve consistently high scores. SelfEQ reinforces self-consistency, accuracy, and potential working vocabulary expansion. To obtain paraphrases, we propose the two-level self-consistency data augmentation strategy using LLM. For a dataset with global captions describing multiple objects, we first use LLM phrase extraction to break them down into object-centered phrases, and then generate paraphrases by replacing primary object while retaining other attributes. Here are two examples. We use LBAP as our base model, tuning it on Visual Genome and Microsoft Cocoa, and evaluating with pointing game accuracy on Flickr 30K and Referit. SelfEQ achieved the best performance among weakly supervised methods and ranked second to gprep on the Referit. gprep uses the custom architecture and clip-based heat map supervision as pseudo-labels. Our method is orthogonal and would possibly benefit from similar supervision as clip was trained on a much larger dataset. Table 2 provides results on RefCocoa Plus. SelfEQ shows significant improvements of over off-the-shelf LBAF and competitive results compared to box supervised method. We assess the impact of data quantity. SelfEQ consistently enhance the performance with more data. Additionally, we test the impact of SelfEQ by integrating equivalent paraphrases as regular image text pairs. Table 3 showed that simply adding image paraphrase pairs without explicit linkage doesn't improve performance. For MFSCOCO, we propose as global captioning to object-central phrases. Table 4 shows tuning with this phrase out both objective, but with SelfEQ, we enhance performance even more. Table 5 evaluates SelfEQ components. Combining LSIM and LCST improve alignment and localization through mutual supervision, boosting self-consistency and accuracy. Here are some qualitative results. On the left, we can see performance in challenging scenarios. Occlusion, small object with complex scenes, object partially shown in the corner, multiple similar objects, abbreviated text. On the right, we have self-consistency with different paraphrases, like terminology, synonyms, regional slang combining with different sentence structures. So for more details, please refer to our paper. Thank you for listening.
Thank you very much, Catherine.
I found it a very interesting direction. One thing that comes to mind is that this might be really useful for domain transfer, like cross-domain adaptation. Have you explored that application?
So we did not propose a general, like a model specifically for visual grounding. So yes, it is possible to apply our model to other domains, but we haven't tried it. So in our test, we only aim to solve the visual grounding. But yes, the way we solve it make it possible, because we didn't really design a method tailored for visual grounding. What we do is to investigate the property, the self-consistency, a general property of vision language model. And we improve the property, thereby enhancing visual grounding. We did see the possibility to transfer it to other domains because we train it on Visual Genome or Microsoft Cocoa. When we do the evaluation, we evaluate on visual grounding data set. So when we do the training, we only use the general image text pairs. And we can see there's definitely a domain shift here.
Yeah, I see. Interesting. And I guess, although you do rely on GradCam quite a bit to actually guide that self-consistency, right? So if that struggles, you may struggle. How good does the initial consistency need to be in order for you to converge? It's hard to measure, but do you have any sense if there are like fringe classes that you don't have a good, like GradCam and your visual model is not going to give a good back projection on? Will it diverge? Did you experience that at all?
Yeah, we actually did. For example, I think Catherine at some point tried Clip, and Clip is not very good, like vanilla Clip, and you try to do some GradCam there, is going to struggle a lot. So then to enhance and fine-tune the model for this task was quite challenging. So it doesn't work that well. It does improve, but it not to this extent. The assumption is to first have a model that will behave well. I believe that this type of approach could be expanded to other models, but we did only show significant performances in Albert. Yeah.
How do the paraphrases actually get generated? I missed that detail. Are these model generated or human generated paraphrases?
So we leverage the LLM to automatically generate those paraphrases. And specifically, there are two different types of data set in general. The first data set is like Visual Genome. It focuses on only a region. So the phrase it will provide us will probably like a cat, a dog. But there's also another type of data set like Microsoft Cocoa. The caption there usually describe the entire scenario, like there are 3 cats sitting there next to a table, something like that. Because we are trained on those general image text pairs, and what we want to do is to improve the visual grounding performance. So we want the model to focus on a specific region instead of the entire image. So for Visual Genome, we already have very short object-centered phrases. They are good to use, but for captions from Microsoft Cocoa, the captions are too general, too broad. It describes the entire scenario. That's not something we want. We have a 2-level strategy leveraging an LLM. For the global captions, we first use in-context learning. We prompt an LLM to extract the phrases from the global captions. So then we have the object-centric captions, either extracted by us or directly from like datasets like Visual Gina. So the second thing we do is to generate the synonyms. There are many ways to generate paraphrases. We can change the entire structure while keep the meaning the same. But we didn't do that because we noticed the self-consistency is actually pretty new concept in vision language model. So we regard our work as the first step to improve self-consistency in visual grounding. So an easier way is to keep all the attributes the same, and we only substitute the head noun in the sentence with the synonym. Because in this way, it's easier to prompt. When we design the prompts for LLM, we only need to do 2 things. First, extract the head noun, and then find the synonym. Otherwise, you have to do some quality control when you do the post-processing for LLM. It'll be more difficult. And the second reason is it will be easier for model to learn because the only difference is actually the head noun. So it will make linkage between the 2 synonyms. They know the sentence structure is actually the same. There's only difference. So they should refer to the same thing. But when we do the evaluation, we actually try different ways. We use some manual generated thing. For example, the example I show in the last slides, there's an umbrella. And the second paraphrase will be, there is a brownie in the image. Brownie is a really uncommon word, and the sentence structure is totally different. Our model still be able to solve this kind of like very difficult scenario.
Another thing is also, Catherine, I think she tried WordNet at some point, right? To try to get these synonyms and all this structure, but it didn't work that well. It's a little bit noisy. It was difficult to parse and to keep the semantics on and so on. So yeah, the large language model prompting actually helped a lot. Yeah.
Yeah, that's great. I was just going to wrap up and just say, I think it's really interesting. I think probably there's a great future in, or future papers in more intricate language grounding, right? And instructional video of how to do certain procedures, or a more descriptive language of what you're seeing in the visual field. But this is a great start. Yeah, thanks.
For practitioners that are looking to apply your findings, what are some practical steps or considerations that they should keep in mind? And if there are any specific scenarios where you think that this methodology shines the most?
I think this method is a great way for practitioners to actually figure out how their model actually behaves, especially because this is not fine-tuned with a specific data for grounded, but it's weakly supervised, right? So if you want to figure out what the model is actually, what are the relations between text and the images or videos or etc., you can take something like this to improve. So you got the GradCam for post hoc evaluation, right? And then you can use this type of technique to expand the vocabulary of your model, or your in-domain model, or out-of-domain model, or whatever you have fine-tuned, and then try to see if the model is actually relying on some spurious correlations. Then you don't want that. You want to have actually the semantics and the descriptions in the text to actually be paired with the objects that you actually want to have. You can use this to figure out if that is happening or not. So for example, yeah, if you care about trustworthy AI, or if you care about the effectiveness of your model, especially in medical domain, for example, or other domains that is very important to find out what the model, the decisions or the inference that is happening there. If you care about that, then I think this is a great method, a great technique. Yeah.
Thank you again, Paola and Catherine, for joining and taking time to chat with us about your paper. Appreciate it.